trying not to expand where your book doesn't, like too much where your book doesn't expand. Okay, so basically we've got a bunch of p orbitals and we can orient them up or down. And these are all of the ways, all the possible ways to orient them if we've got 1,3-butadiene, so we've got 4 p orbitals. Which basically ends up with different nodes. So wherever these guys are all the same color, these are the p orbitals. This is the atomic orbital diagram. This is what the molecular orbital looks like. So whenever they're the same polarity, there's smushing, smearing. So bonding orbital, right? And we've got bonding and anti-bonding orbitals. Do you guys remember? Do you remember doing something like, let's see, 2s, 2p, yeah, this, the molecular orbital stuff where we take the atomic orbitals, we do maybe O2. So oxygen has 6, 1, 2, 3, let's try this way. 3, 4, 5, 6, and we have to fill them in like that, right? We don't pair them first because that's higher energy. 1, 2, 3, 4, 5, 6, and then we have molecular orbitals in the middle. These are atomic. These are molecular in the middle. So these guys combine to make 2 because, well, we put 2 in, we get 2 out. We have sigma and sigma star, right? Bonding, anti-bonding. So these guys do the same thing, but you end up, oxygen might be the one where it's like this. Something like that. Whichever shape that's supposed to make. This is these guys. These like pi and pi star. This guy is a bonding orbital, pi orbital. This next one, where we have only 1 node, the more nodes we have, the higher energy that bonding orbital is. So the next one with only 1 node right here looks like this, right? And that is also a bonding orbital. After that, we have just my inability to work a clicker. It's fine. After that, we make one with 2 nodes, and so this guy's an anti-bonding orbital. Yes, it does look like right in the middle there, we've got, like over here, we've basically got, it's almost a p orbital on either end, right? Because like, there's a node just separating this guy over here. But overall, this is like the shape of the pi molecular orbital. But in the middle, we've got the smearing of these 2. So it kind of looks like we've got a bond forming here. This is still an anti-bonding, which is weird. Yes?
What is the anti-bonding orbital?
Anti-bonding orbital is basically an orbital, so these aren't all full, right? Theoretical. I'm trying to think of a way to describe. You know, sometimes when you get asked to describe, like to define something that you totally know what it is and you're like, God, can I even define that? Let's see if this gives us a nice. Oh, okay. An antibonding orbital orbital is a molecular orbital containing electrons outside the region between the two nuclei. That's not exactly, well, I mean, that's not, that works for sigma, but like that doesn't work for pi antibonding orbitals, so, well, okay, I guess outside the region between the region of bonding, I guess, and in this case we've got, basically, if we have electrons in these orbitals, it's not contributing to holding everything together, and it's, I don't say it's pushing everything apart, but it's certainly not helping. Like if we have the same, like when we fill this in, that helps us determine the bond, like how many bonds are between each oxygen, right? So these are full. 2, 4, 8, 1, 2, 3, 4, 5, 6, 7, 8. So we have these guys cancel out because whenever we have pi bonds and sigma bond, or whatever we have a bonding and an anti-bonding, they cancel out. Neither of them net contributes to the bonding between these. And then we've got this happening. So this is I mean, those are unpaired, but what is that, a 2.5 bond it's trying to tell me? Wish I had just picked nitrogen, because then we'd have nitrogen has one less on each. So we end up here, and I don't have this problem. So I don't have to remember whatever weird exception oxygen is. So if we started with nitrogen, we had 5 to begin with. We got here, these guys cancel each other out, and we've got 1, 2, 3 full bonding molecular orbitals, and then none of these guys are full at all, so nothing canceling out here. Nitrogen, triple bonded to nitrogen, and that kind of, that. Just gonna pretend we didn't do oxygen, and I'll look that up later, and if you're curious, I'll do that. But basically, yeah, there's just sort of these theoretical places, because like the bonding orbitals are just these like, it's this weird peak, like physical chemistry statistics thing where you put in a bunch of equations that are inherently unable to be solved, and if you do a series approximation that's supposed to get close to what the answer would be if it were somehow solvable, it makes shapes, right? That's where the VSEPR like atomic orbitals came from, and this is sort of, you can do similar things and get calculations of these.
Yeah, that helps.
Okay,
Yeah.
okay. Sorry, it's very, very p-chem. Anyway, we can just do it by drawing p orbitals and alternating, flipping them so we have different amounts of nodes. And then we can arrange these in order of energy, because no nodes, low energy. All the nodes, high energy. And then with this guy, 1,3-butadiene, how many pi electrons do we have?
2 or
4, right? Yeah, 2 bonds, 2 pi bonds, so 4 pi electrons. So then we just fill them in, kind of like we did over here in this mess that just, you know, doesn't need to live here anymore. So we fill them in, 2 down here, 2 here, and we have none left. So, cool. We filled up this bonding orbital and this bonding orbital, and we don't have other ones hanging out in non-bonding orbitals. That pretty much makes sense because, I mean, well, I don't know, bonding orbitals, like with carbons and stuff, that's what we do, right? Like we don't have lone pairs, we don't have things like extra electrons to hang out. Carbons bond to 4 things, or make 4 bonds at least, so everything's gonna be contributing to bonding. But this guy, we'll talk about that in a little bit, but this guy, for future reference, we're going to talk about HOMO and LUMO. Have you guys heard this term before? Okay, HOMO is the highest occupied molecular orbital. So these are your molecular orbitals. This one's occupied, this one's not. So this is the highest energy occupied molecular orbital. Occupied, it has electrons in it. LUMO, lowest energy unoccupied molecular orbital. So basically, we're going to skip through the next couple slides, but we're very close to talking about UV vis spectroscopy. We're going to talk about that depending on how many slides I want to fly through. We're going to talk about that in a couple slides. So that has everything to do with just these two. Like, you can do a bunch of PChem and you put a bunch of, I don't even know because I've done a bunch of these calculations, but I use Gauss view, so I just like click and draw molecules and then tell it, yeah, go to the lowest energy. All right, yeah, tell me what the electrons do, and it does it. And I don't know how to code, but it gives you things like this. The only two we end up caring about are these guys. Highest occupied molecular orbital, lowest unoccupied molecular orbital. And the energy gap between them is important. Fine. We'll do that reaction before we start talking about LUMO and UV vis. So basically, if there's some way, for some reason, I'm trying to think of a reaction where we can end up with a double bond here, moving to here, and back and forth. I'm not seeing that as a reversible reaction. So I guess they're just saying theoretically, or there's just one that I don't remember. But basically, which one of these is more stable? This guy, right? Because this is conjugated. This is not. Yeah? Okay. Sorry, I just started using terms that, because I don't teach first semester, I forget which things you guys have heard before. There we go. So there's additional stability to dienes when we've got them conjugated versus when we don't. Fine, let's do this reaction. So you guys have done the reactions before with alkenes, where you have an alkene. Fine. Wait, maybe it's because the other marker's the good one? Yeah, all right. Where we've had like this, and we react that with HBr or this way, or we react with Br2, right? You remember this? This is a thing that happens, so you get this guy going, hey, give me that. And it's like, all right, fine. And then later this comes in and attaches to one of them. I want to say you get the hydrogen here. Yeah. The first addition is going to be, there were already two hydrogens, and now we have a third hydrogen. And then we get a positive charge on here, right? And we have the positive charge here and not here because it's more stable here, just because it's more substituted. It doesn't have anywhere to go resonance-wise, but that's because we don't have conjugation yet. Then this guy comes in, and we get, I guess really we only need to draw that. That's the product for this guy, and this guy, well, you have that to be. You do the same thing, but both of the things you add are bromines, so you don't really have to pay attention as much to the order in which you add things, and you get this. We can do a very similar thing with dienes, except when they get to that charge stage, they can do some stuff if they're conjugated. So we're gonna have this, and to add HBr, that's gonna be at negative 78 degrees Celsius, or at least if we do this, we get a mixture of two constitutional isomers. So if we cool this down to really cold, and we do this with HBr, okay, yeah. Then we end up, never mind, this is a lot of bond breaking, and we're just gonna draw everything out. No, 2 hydrogens, not 1. That gets 1 hydrogen, that gets 1, that gets 2. There we go. All right, we're gonna draw it out like this. So we do a similar kind of thing, or we're going to attack, and that's going to go here for a couple reasons, but for similar reasons to the other one, because at the very least, the charge is going to be more stable. Let's see. Okay, we get this, right? But it doesn't have to live like this, right? So I don't want to draw out all those. I'm going to draw them here. Why are you getting stuck? I'm sure that once somebody gets used to this, it's really nice to be able to just push it down with your foot. But man, I wish it were not so easy to do accidentally. I'm going to do resonance this way because that's a lot of drawing. So what we have right now is this, right? And we've got a ton of resonance we can do. We can go, well, okay. We've got some resonance we can do. We can do this and put the plus over here, right? And can we get the plus to go on here? Well, we can try, but really the only other thing we can do is do this. And do that, right? So this guy is going to have a partial negative charge, no matter where he is on here, partial negative, right? Because overall we've got a cation, so more negative than the other ones. These guys are partial positive charges, but they both share partial positive charge, which makes this guy even more stable than just when we broke the single one, right? Because now we've got this guy, it's partial positive. We've got, sharing. So, sharing of the discomfort. That means that we have 2 outcomes. Let me just draw. Okay. So we've got both of these, and we've got and we can react either one of them. If we have this one, if we primarily look like this, or our charge primarily looks like this, we can attack there and form I hate drawing all these hydrogens. We can form this, right? And here, we could attack here and form that. this with bromine, diatomic bromine Br2. We just have a di substituted, right? We have bromine here and there, and we have bromine here and there. It's just, I think, more useful to use HBr so that we remember which one gets added first, right? But we can go, let's call this deuterium bromide, and we can tell both of the things that were added on there. Yeah. Okay, so what are we gonna get? We get a mixture at negative 78 Celsius, right? So we can get both. How do we decide which one's favored and which one's not? Well, if nothing's favored, we'll get like a 50-50. Six-minute timer, so it tells me again to shut up. Okay. If neither one is favored, right, then we end up with a 50-50 mixture. We don't. We get like 90% this one, and no, JK, 90% this one. Yeah. And 10% that one. If we do this at negative 78 Celsius, and if we do bromine, just bromine addition, we also favor the one where these guys are right next to each other, right? And if we do this at very cold temperatures. Just did the mechanism. Go ahead and take a break, because this is slightly